Hi, everyone. Before one can understand the way modern physicists think about particle physics, one needs to review the wave-particle duality. Now, in this video, I am assuming that viewers already have some experience with the wave-particle duality from, for instance, a upper division course in modern physics. So in this video, I'll just be reviewing really the main ideas of the wave-particle duality and discussing some of the experimental evidence for this duality. All right, so I can get my slide to change. All right, so to understand the wave-particle duality, we first need to think about a classical wave versus a classical particle. So when we say the word particle, what do we mean? And when we say the word wave, what do we mean? And specifically, what did we mean when we said the word particle or wave before we knew about the wave-particle duality? And so what I'd like you to do is to pause this video and name at least two ways you can distinguish between a wave and a particle, or at least, think about two ways that you might distinguish between these two things. So pause the video and then restart it when you have an idea about this. All right, so there are lots of ideas that you might have come up with. So here are some of the ways that I think about a classical particle versus a classical wave. So particles are maybe easier. They're pretty familiar to us. We all have something in our mind we can think about when we think about a particle. Most of us perhaps picture like tiny little billiard balls, right? Little specks of dust bouncing around. And things that we know about these objects is that they're going to move in a straight line unless if they're acted on by a force. So this is thanks to Newton's laws. This is the way particles behave. Particles are going to be blocked by barriers. They can't go through them. And if there's a hole in such a barrier, they're going to go straight through that barrier and keep moving in a straight line, again, unless if there's some external force acting on them. And the way we mathematically describe particles is as if we have a stream of particles, we would describe that stream by some individual particle number, and each particle can have its own particle energy. And so we think about these discrete objects when we think about particles. Now, what about a wave? Waves are very different types of objects. So we learned from introductory physics that waves can interfere with each other, and these result in interesting interference patterns. So you can imagine, for instance, if we have ripples on a pond, maybe you dropped a stone in the pond or something, it causes some ripples. And then if I drop two stones in the pond, those ripples are going to interfere with each other. High points will add with high points, low points. If we have another low point, we'll make them even lower. But then a high point and a low point can sort of even each other out and balance each other out. So you end up with these really interesting interference patterns when you have objects that behave like waves. Waves can bend around barriers. So if we, again, imagine we have some barrier that perhaps has a hole in it, allowing a wave to go through, the wave will go through and it will spread out after going through this hole in a barrier. And then finally, the way we mathematically describe a wave is going to be very different. We don't think about waves as being these discrete objects. Instead, waves are continuous objects that are described by some amplitude and perhaps a wavelength or a frequency. And these are the ways we think about waves. So what's the wave-particle duality? Well, this comes from the question, let's say, for instance, is light a wave or a particle? We physicists historically did not know a priori whether we should describe light as a wave or a particle. And in fact, as far back as Newton, he thought light was made up of particles that he called, I think, corpuscles or something like that. Light he thought of as this stream of particles, not as a wave. So how can we determine? Well, we do experiments and we see, does this object that we're studying, in this case light, have more wave-like properties or more particle-like properties? And one of the obvious things we can do is see how does this object behave if we send it through a barrier. And so one of the early famous experiments that really taught us that light can behave like a wave is known as the double slit experiment, Young's double slit experiment, where he sent light through a barrier with two slits in it and saw that the pattern that the light had on a screen after the barrier is indeed an interference pattern that you would expect from wave-like behavior. And so this, combined with Maxwell's equations, gave us a mathematical description of electromagnetic waves, which we understand to be light. And so this experiment, along with Maxwell's equations, really solidified wave interpretation of light for a little while, until we had the photoelectric effect, which is a very famous experiment that, in fact, Einstein won the Nobel Prize for. He didn't win it for general relativity. Instead, it was for understanding the photoelectric effect, which taught us that light can also be thought of as a particle, where it is better described as made up of a stream of photons, where we aren't thinking about an object that has some amplitude and some frequency or wavelength, but instead we're thinking of these little packets of energy that are more like particles, where we have a certain number of photons, which again is the name that we have for a particle of light. We have a certain number of photons, and each photon has a certain energy. And thinking about light that way was what allowed us to better understand the photoelectric effect, which I'm not going to go into the details of because, again, I'm sort of assuming that you've heard of this before, and I highly encourage you to read up on it if it's been a while and you don't quite remember what the photoelectric effect is. It's a very interesting experiment and very important to have in the background of your mind as a physicist. So light, from these two different experiments, in one case, we're describing it as a wave, and in another case, it seems to be behaving like a particle. What about electrons? We definitely, when you first learned about electrons in your chemistry class perhaps, you thought of them as particles. You probably had the Bohr model of the electron in your mind, or the Bohr model of the atom, excuse me, in your mind, where you had some nucleus with electrons orbiting the nucleus, sort of like our planets orbit the sun, right? So you imagine these little tiny flecks, or tiny billiard balls orbiting the nucleus. And so probably if someone on the street asked you, is an electron a particle? You would have said, yeah. Or if someone said, what's an electron? You'd say, oh, it's a tiny particle, right? But maybe you didn't know until your modern physics class that an electron can also be thought of as a wave. So again, how do we know electrons are waves? Well, again, we can actually do the same double slit experiment that we did with light, but instead with a stream of electrons. And we will, in fact, see that the electrons form an interference pattern in exactly the same way light does. And so they don't appear to be going through our barrier like these tiny little billiard balls where they go in straight lines. Instead, they seemed to go through our slits and then spread out afterwards and interfere with each other. So we get an interference pattern that we definitely associate with a wave-like behavior. Now, if we slow this experiment down and send in the electrons, maybe one at a time, rather than in this continuous stream, and we introduce some little detectors at each slit. So we actually are saying, okay, if I'm looking at each electron as it passes through this slit, which slit is the electron going through? And here we're really, in order to even ask that question, we're really thinking about the electrons as particles. We're saying, which little particle of an electron, which slit is each electron going through? If you do that, the interference pattern actually disappears. And instead, you end up with two stripes of electrons that end up on your screen, your detection screen, which is exactly what you would expect if electrons behave more like particles, right? We don't end up with our interference pattern is totally washed away, and instead we just have two images of our slits that appear on the screen. And so here we're seeing that electrons are behaving more like particles. So at the end of the day, what we now understand is that all fundamental particles can be thought of as having both a sort of traditional classical particle-like behavior and a wave-like behavior, right? So, and that's really what the wave-particle duality is. It states that objects classically described as waves, like light, can also be described as particles. In the case of light, these are referred to as photons. On the other hand, objects that perhaps classically we thought of as particles, like electrons, can actually also be described as waves. And so in quantum mechanics, you might have learned that you can describe an electron, the position of an electron by a wave function, right? Rather than saying the electron is at one point in space, we have some wave function that is describing a probability distribution for where the electron might be. And really, this isn't special to light and electrons. In particle physics, this wave-particle duality is fundamental to all of the fundamental particles. And the framework that modern physicists use for particle physics reflects this dual behavior. So it's very important to have in the back of your mind when thinking about our modern description of particle physics. So that's the wave-particle duality.